Good day and welcome once again to our today's class on real analysis. In today's class, we'll be talking about the Cauchy sequence. Remember, in our previous lesson on sequence convergence, we have said that a sequence is said to be convergent if it has a limit. And then, using the epsilon definition, we said a sequence is convergent if for any epsilon greater than 0, there exists a k belonging to the set of natural numbers such that the absolute value of an minus L is less than epsilon for all n greater than or equal to k. We described sequence convergence using the limit. Recall that we have been describing sequence convergence or the convergence of a sequence using the limits of the sequence. And that was why when we defined sequence convergence, the epsilon definition of sequence convergence, we say a sequence A sub n is said to be convergent if for every epsilon greater than 0, there exists a k belonging to the set of natural numbers such that A sub n minus L, the absolute value of A sub n minus L, is less than epsilon for all n greater than or equal to k. But the Cauchy sequence tries to characterize sequence convergence without using the limit of the sequence. It characterizes the sequence convergence without using limit. Let's take, for example, consider the sequence A sub n equals the reciprocals of number. The terms of this sequence are what? 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and it continues like that. We see that as n goes bigger and bigger, this sequence tends towards 0. Therefore, we say that the limit of the sequence is 0. And that also implies that the sequence A sub n converges to 0. This sequence now, characterizing convergence without using limits, means that we want to consider the relationship between the terms of the sequence. And if we are still using the sequence of reciprocals of numbers, again, our terms are what? 1, 1 over 2, 1 over 3, 1 over 4, and it continues like that. We see that as n gets bigger and bigger, the terms of the sequence get closer and closer together, or to each other rather. And that brings us to our definition of Cauchy sequence. That a sequence A sub n is said to be Cauchy is said to be Cauchy if for any epsilon greater than 0, there exists a p belonging to the set of natural numbers such that a sub m minus a sub n is less than epsilon for all m and n greater than or equal to p. And by that, we have defined the Cauchy sequence. We will take an example and try to prove whether the sequence is Cauchy or not. Let's now look at the same sequence of reciprocals of number. We want to determine whether the sequence is Cauchy or not. Prove that a sub n equals 1 over n is a Cauchy sequence. The first thing we need to do is to recall our definition of Cauchy sequence. Recall that a sequence a sub n is Cauchy if for every epsilon greater than 0, there exists a p belonging to the set of natural numbers such that a sub m minus a sub n is less than epsilon for all m n greater than or equal to p. Then the next thing we need to do is to identify a p that works. To identify a p that works, we begin from the absolute value of a sub m minus a sub n. But our a sub m is equal to 1 over m, since a sub n is 1 over n. So we have the absolute value of a sub m minus a sub n to be equal to the absolute value of 1 minus m, 1 over m minus 1 over n. And that gives us 1 over n, m, plus minus 1 over n. And by the time we use triangle inequality on that, it gives us 1 over m plus minus 1 over n. The absolute value takes care of the minus. We have 1 over m plus 1 over n. But we want this to be less than epsilon, as stated in our definition. We want a sub m minus a sub n to be less than epsilon. Therefore, we say let 1 over m be less than epsilon over 2 and 1 over n be less than epsilon over 2. That implies that what? 2 is less than m epsilon, and that means that what? Our m is greater than 2 over epsilon. That is, 2 over epsilon is less than m. And the same thing will happen for n. Similarly, 2 over epsilon will be n. But since m and n are greater than p, it further implies that our p is greater than or equal to 2 over epsilon. So we can go ahead to prove now. Now we are proving. We need to make certain assumptions. Let epsilon be greater than 0 and p be greater than or equals to 2 over epsilon. Therefore, a sub m minus a sub n is equal to 1 over m minus 1 over n. And if we do the same thing we did there, and that is less than or equal to 1 over m plus 1 over n, but m and n are greater than p. Since p is greater than 2 over epsilon, it implies 2 over epsilon will be less than m, and similarly 2 over epsilon will be less than n. So the absolute value of a sub m minus a sub n less than 1 over 2 over epsilon plus 1 over 2 over epsilon. That is less than epsilon over 2 plus epsilon over 2, and that is less than epsilon. Therefore, the sequence is a Cauchy sequence. We take one more example and we try to show that the sequence is Cauchy. Prove that the sequence a sub n equals n over n plus 1 is Cauchy. Remember, we said the first thing we need to do is to recall our definition. Recall that a sequence a sub n is Cauchy if for every epsilon greater than 0, there exists a p belonging to the set of natural numbers such that a sub m minus a sub n is less than epsilon for all mn greater than or equal to p. And we said to show that it is Cauchy, the first thing we need to do is identify p. And we begin by using a sub m minus a sub n. Our a sub n is n over n plus 1. Therefore, a sub m will be m over m plus 1. And therefore, a sub m minus a sub n becomes m over n m plus 1 minus n over n plus 1. And that gives us m into n plus 1 minus n into n plus 1 all over n plus 1 n plus 1. And so that is equal to mn plus m minus m nm minus n over n plus 1 into n plus 1. And so this cuts this. We are left with m minus n over n plus 1 into n plus 1. Now, assuming n is greater than m, then we know that what? The absolute value of m minus n into n plus 1 n plus 1 is less than m over m plus 1 n plus 1. And also, m over n plus 1 is less than 1. So what does this imply for us? It implies that the absolute value of a sub m minus a sub n to be m minus n over n plus 1 n plus 1 is less than m over n plus 1 n plus 1 and this will be less than m over m plus 1 into 1 over n plus 1. But this is less than 1. So this is less than 1 into 1 over n plus 1. That is less than 1 over n plus 1. Therefore, let 1 over n plus 1 be less than epsilon. But n is greater than p. It implies that p is less than n. Therefore, 1 over p plus 1 will also be less than epsilon. Therefore, we go ahead to state the proof. So let epsilon be greater than 0 and p such that 1 over p plus 1 is less than epsilon. Therefore, a sub n minus a sub n will be equals to m over n plus 1 minus n over n plus 1. And that is equal to m minus n over n plus 1 n plus 1. And this is less than m over n plus 1 n plus 1. And this now, as we saw here, is less than 1 over n plus 1. But n is greater than p. And we have said that p is less than n. Therefore, it means that this will be less than 1 over p plus 1. And that is less than epsilon. Therefore, a sub m minus a sub n is less than epsilon. And that implies that the sequence a sub n is Cauchy. If you have gained anything from today's video, give it a thumbs up, like, and share with your friends and colleagues. Thank you. God bless you. I see you in the next video where I'll be talking about other examples on Cauchy sequence.